Hello, welcome to this short introductory course on elementary particles and the Standard Model. My name is Walter Urbaniak. I'm a retired computer networking engineer. I have an interest in physics, and particularly quantum mechanics, but I'm not a physicist and not a professor. This is a 3-hour introduction to elementary particles and the Standard Model. This class is targeted at people who are not physicists but have an interest in physics. The transcript for these lectures is available as a PDF. The link is available in the description of the YouTube video. The material in this course on light and atoms is covered more thoroughly in this other course of mine. The course is divided into two 80-minute videos. The material is divided into 35 sections. After any section, you could pause and resume at a later time. Here's the roadmap for the course. We will cover a lot of material, but only at an introductory level. Much of this may be new to you. Some ideas will be complicated or confusing. Don't worry about following every detail of things that are completely new to you. You will still learn some new concepts and terms and get a glimpse of one level of the reality of our universe. I am not an expert. I've never taken a course on elementary particles. Most of this information comes from reading articles on Wikipedia, which I list at the end of the documentation. There are 17 elementary particles, or fundamental particles, in the Standard Model. Elementary particles are subatomic particles with no substructure. Do not confuse this word elementary with the chemical elements. The elementary particles are shown in this diagram, which we will explore. But first we will cover atoms. Then we will return to this diagram. Most images used in this presentation came from Wikipedia. I will give attributions in the lecture script file. We will start with the atom and key quantum mechanical principles which apply to elementary particles. Then we will cover the elementary particles, then composite particles, protons and neutrons, and nuclear fusion in the sun. Then light, photons, and two-slit diffraction and interference, and finally, beyond the Standard Model. Here is a highly stylized representation of a lithium atom. In the center is the nucleus. There are 3 electrically positively charged protons, shown as red spheres, for this lithium atom. There are 4 electrically neutral neutrons, shown as black spheres. Outside the nucleus, there are 3 electrically negatively charged electrons, shown as blue spheres in circular orbit around the nucleus. The number of electrons equals the number of protons. The number of protons dictates the element. In this case, 3 protons is lithium. Most or many adults recognize this stylized representation as an atom, which is the justification for this useful stylization. However, almost everything is wrong with this picture as a physical representation of an atom. The electrons are not in circular orbits around the nucleus. We will return to this. The electrons are elementary particles that are point-like, with size less than 10 to the minus 22 meters, 1,000,000 times smaller than a proton. Electrons are not little spheres. High-energy electrons have been smashed into one another in collider experiments, and there has never been any evidence of size, radius, volume, or internal structure. Electrons are point-like elementary particles, not little spheres. None of the particles in atoms have any colors like this representation. It turns out that protons and neutrons are not elementary particles. Each consists of 3 quarks and a sea of gluons. Quarks and gluons are elementary particles, as we will see. Protons and neutrons are composite particles, not elementary particles, as far as a particle physicist would categorize them. However, to a chemist, protons and neutrons are elementary as far as chemistry is concerned. You may have learned in school that protons and neutrons are elementary. In low-energy collisions, protons and neutrons behave like billiard balls, so we won't quibble with representing them as spheres here. Protons and neutrons do have a size of about 0.8 femtometer radius, 0.8 by 10 to the minus 15 meters, whereas the radius of the lithium atom is about 150 picometers, 1.5 by 10 to the minus 10 meters, or about 1.5 angstroms. So the nucleus is about 100,000th, 10 to the minus 5, the radius of the atom, or 10 to the minus 15 of the volume. Too small to represent at the same scale. Electrons and all particles and objects with mass are constrained by the quantum mechanical principle called Heisenberg's uncertainty principle. The uncertainty in position times the uncertainty in momentum, which is mass times velocity, must always exceed a certain minimum value. Uncertainty in position times uncertainty in momentum greater than or equal to this value. This formula is for a particle or object moving much slower than the speed of light, which is true for most electrons in atoms. The value on the right-hand side is called h bar over 2, where h bar is the reduced Planck's constant, but we won't need to know this for this class. This relation constrains how well we can ever possibly know or measure a particle or object's position and momentum simultaneously, regardless of technological ability. If we want to measure a particle's position very precisely, small uncertainty in position, we lose the ability to simultaneously know or measure precisely its momentum or velocity in that direction, and vice versa. Classical mechanics assumes that we can, if we wish, measure the position and velocity of any object perfectly precisely. If we also know the forces acting on the object, then we can integrate Newton's equation, force equals mass times acceleration, and we can calculate the object's velocity and position perfectly for all time. So we can know its trajectory perfectly for all time. For example, perhaps its trajectory is a perfectly circular orbit. But physicists know now that this classical assumption is wrong at the scale of electrons in atoms. We cannot simultaneously know or measure a particle or object's position and momentum precisely. Either we don't know the position well or we don't know the momentum well. This means that there is no precise trajectory and no precise orbit. For an electron bound in an atom, actually we cannot identify any trajectory at all for the electron. Instead, we can use quantum mechanics to identify the probability for the electron to occupy each position in space. This is shown in the following probabilistic cloud representation of a helium atom. The gray shading represents the position probability density for the two electrons. Highest probability near the nucleus, probability density falling off with distance, less probable with distance. No circular orbits, no hard boundary, but there is a probabilistic size to the atom. Heisenberg's uncertainty principle and quantum mechanics prevent the electrons from simply collapsing into the nucleus and prevents atoms from collapsing together. They give atoms their size. Changing topic, quite naturally we think of elementary particles such as electrons as like billiard balls. Physicists can collide them into one another. However, physicists now know that electrons and all particles with mass are quantum mechanical particles that sometimes exhibit wave-like properties and sometimes exhibit particle-like properties. And this is called wave-particle duality. A particle with mass has a wavelength that is inversely proportional to its momentum, given by the Debris wavelength of the particle. Wavelength lambda equals this quantity in the numerator, which is Planck's constant, divided by the momentum, mass times velocity. It turns out that for an electron bound to a proton in a hydrogen atom, the electron's momentum is such that its wavelength is comparable to the size of the atom. So, along with the Heisenberg uncertainty principle, the Debris wavelength of the electron gives the atom its size and its lack of circular orbits. Protons and neutrons also have Debris wavelengths. So do individual atoms, molecules, and even a baseball. Toward the end of the course, we cover light, photons, and two-slit diffraction of both photons, electrons, atoms, and molecules acting as waves. The Debris wavelength is only a rough tool on the way to quantum mechanics. When the Debris wavelength for a particle or object at some momentum is much smaller than the size of the object, as it would be for a baseball or a bacterium, then we're probably safe to use classical mechanics for the object's position and velocity. When the Debris wavelength for a particle or object at some momentum is comparable to or larger than the object's size or spatial locus or the size of slits the particle is passing through, then classical mechanics might not be safe or correct or applicable, and we should seek a quantum mechanical solution. For an electron bound in an atom, its momentum is generally such that its Debris wavelength is comparable to the size of the atom or the size of the electron orbital, and so we should use quantum mechanics and get a wave function solution and a probability density description of the electron's location in space. We cannot use classical mechanics and there is no trajectory, no orbit. In this course we will not be doing any quantum mechanics, so don't worry about that. So the utility of the Debris wavelength calculation is really only to distinguish where we should use quantum mechanics and get a probability description from where we are probably safe using classical mechanics and getting a classical trajectory. So don't think of these Debris wavelengths as being spatial oscillations like the standing waves of a guitar or piano string. And if you know of Bohr's early model of the electrons in atoms and maybe learned about electron waves around a circular orbit, this is wrong and misleading, and feel free to contact me for better info. And for these matter particles, don't think of these waves as traveling waves or as having frequencies as a light wave would have. This is all you need to know about Debris wavelengths, and actually we'll not be using this concept further in this course, and we will not use quantum mechanics. So if this level of understanding is frustrating, put this aside and don't let it impact thinking about the next material. Indistinguishable particles and spin. All electrons in the universe are identical. They have the same mass and electrical charge. If we bring two electrons close together, it becomes impossible to tell which is which. We cannot mark them with colors or numbers to tell them apart. They are indistinguishable particles. Likewise, two protons are indistinguishable. Two neutrons are indistinguishable. Each elementary particle is indistinguishable from others of the same type. Electrons, protons, neutrons, and all but one of the elementary particles have an unusual built-in property called intrinsic spin angular momentum. If the particle were a tiny sphere, which it's not, we would say that the sphere is always spinning around some axis in space at a constant rate. However, the elementary particles are point-like, not spheres. They are not spinning, but they always carry a fixed amount of spin angular momentum. This is a consequence of quantum mechanics and special relativity, and we don't need to understand this fully. Visualizing intrinsic spin angular momentum is a real challenge for point-like particles. Don't worry about this visualization. Or if you must visualize, think of them as the smallest possible spheres that we can never ever measure their size, though physicists know definitely that they are not little spheres. We will learn a little more about spin for two reasons only. We will see that two electrons can occupy the same spatial wave function or orbital. And we will see that all elementary particles get divided into two categories based on their spin: fermions and bosons, whose behavior is different and significant. After that, we won't be using spin further, so don't worry about visualization. Intrinsic spin angular momentum is a built-in physical, mathematical, quantum mechanical property of point-like elementary particles. Don't try too hard to visualize it as spinning in space. It is just a given property of particles. For the electron, we can choose any axis in space and then measure the spin angular momentum component along that axis. And we will always find that the angular momentum is completely aligned parallel to that axis, which we call spin up, or is completely aligned anti-parallel to that axis, which we call spin down. These are the only possible outcomes, no matter what axis we choose. The electron spin is a two-state system, and this is called spin 1/2. The intrinsic spin angular momentum component magnitude is 1/2 times the constant h bar, the reduced Planck constant. But this is not important to this class. Particles whose spin is half of an odd integer, for example 1/2 or 3/2, are called fermions. We say that the electron is spin 1/2 and is a fermion. 12 of the 17 elementary particles are spin 1/2 fermions. Protons and neutrons are also spin 1/2 fermions, even though they are not elementary particles. Total angular momentum is conserved in all interactions and is an important quantity. However, for this course, we only needed it, angular momentum, to get to fermions and bosons. Electrons have electrical charge and spin, and together these make the electrons tiny permanent magnets. This property is called magnetic dipole moment. It is the magnetic dipole moment of electrons that makes iron a ferromagnet. The electron's magnetic dipole moment can be very accurately measured and very accurately calculated from quantum electrodynamics computer calculations. And the two results agree to 13 significant figures, the most successful result of any scientific theory and experiment. Physicists call this experiment G-2. Protons are also tiny permanent magnets and are the basis of medical magnetic resonance imaging MRI machines. Neutrons are also tiny permanent magnets, even though they have zero net electrical charge. Electronic energy levels in atoms. Electrons bound in atoms can only be in specific, definite, quantized electronic energy levels. These energy levels are specified by quantum mechanics. Here is a representation of the electronic energy levels for a carbon atom. Carbon has 6 electrons. At low temperatures and ordinary temperatures, the electrons want to occupy the lowest energy levels possible. Will all 6 electrons occupy the ground state? No, they cannot. Electrons, and all particles that are fermions, obey the Pauli exclusion principle. At most, one fermion, for example, electron, can occupy a single quantum state. For our diagram of energy levels for the carbon atom, each horizontal line represents 2 quantum states. But if both states are occupied, those 2 electrons must have opposite spin. Following is the lowest energy state for the 6 electrons of a carbon atom. The 1s ground state and the 2s state are each occupied by 2 electrons of opposite spin. One spin up, one spin down. 2 of the 2p states are occupied by a single electron, which we're showing as spin up. You see that there are 6 electrons. 1, 2, 3, 4, 5, 6. The p atomic orbitals are directional, with highest probability along an axis, not spherically symmetrical. Here is the p sub z orbital. It's oriented along the z-axis. Here is a different representation of the p sub z, p sub x, and p sub y orbitals. The p sub z orbital is 2 gray lobes in the z-axis. The P sub x orbital is 2 orange lobes in the x-axis. The P sub y orbital is 2 green lobes in the y-axis, whereas the 1s orbital and 2s orbitals are spherically symmetrical. Molecular orbitals between pairs of bonded atoms are also directional. If electrons did not obey the Pauli exclusion principle, all electrons would bunch together in the ground state, the 1s orbital. Then chemistry, biology, material properties, and electronics would not exist. Protons and neutrons are also fermions and obey the Pauli exclusion principle for occupancy of their energy levels in the nucleus. The standard model of elementary particles. 12 of the 17 elementary particles are spin 1/2 fermions and obey the Pauli exclusion principle. 5 of the 17 elementary particles have spin 1 or 0 and are called bosons. Multiple bosons can occupy the same state simultaneously, unlike fermions. In fact, bosons prefer to bunch up into the same state when they can. Laser light is an example of photons bunching up. Bosons do not obey the Pauli exclusion principle. Here is the standard image representation for the standard model of elementary particles. The 17 elementary particles are placed in 4 rows and 5 columns. Let's start with the electron to see what a cell contains. First column, third row. Electron, its symbol is E. There are 3 numerical values in the upper left of the cell. The top value is the mass of the electron, 0.511 million electron volts divided by the speed of light squared, which is to say that its rest mass energy is about 500,000 electron volts. Now, you are not familiar with these units, but the electron mass is roughly 1/2000th the mass of a proton and 300,000 times more than the energy of a photon of red light. The second number is the electrical charge, which is -1 elementary charge unit for the electron. Electrons have the lowest mass of any electrically charged particle of any type. The third number is the intrinsic spin angular momentum, which is 1/2 for the electron. The 3 columns to the left all have spin 1/2. Each of these is spin 1/2. These are the 12 fermion elementary particles, which obey the Pauli exclusion principle. Look at these 12 cells and notice that all 12 of these particles have non-zero mass. These particles always travel at less than the speed of light. The three columns are called the three generations of matter: 1, 2, and 3. Within a row, the three columns have the same value for electrical charge. In this row, the electron, it's -1, -1, -1. And the mass increases from left to right: smaller, medium, large. However, there is no nice formula for calculating the masses. The masses are a mess, and they are what they are. There are four fundamental interactions in the universe that can act on some or all elementary particles: gravitation, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravitation acts on all particles and all objects, even those with zero mass, and the force carrier is called the graviton, which is presently hypothetical. It's not yet been detected. Electromagnetism operates on all electrically charged particles, and the force carrier is the photon. The strong nuclear force, also called the color force, acts on quarks and gluons, and the force carrier is the gluon. The weak interaction acts on quarks and leptons, and the force carriers are the W+, W-, and Z bosons. The two columns to the right of the elementary particles chart are the boson particles that carry forces and interactions between particles. The orange column is 4 boson particles with spin 1. These are called gauge bosons or vector bosons. The gluon and the photon have 0 electrical charge and 0 mass and travel at the speed of light. The gluon mediates the strong nuclear force, also called the color force, between quarks that holds a proton together and a neutron together, per quantum chromodynamics. Gluons glue quarks together. The residual strong force attraction between protons and neutrons in a nucleus is not elementary. We will cover this later. The photon mediates the electric and magnetic forces between electrically charged particles per quantum electrodynamics. These 9 fermions have electrical charge and are affected by electromagnetism. The W boson also has electrical charge. A photon has energy that is inversely proportional to the wavelength of light or electromagnetic radiation. Photon energy is Planck's constant times the speed of light divided by the wavelength of the electromagnetic radiation. When an electron bound in an atom drops from a higher energy level to a lower energy level, the atom emits a photon with energy equal to the difference in energy levels. When an electron gets excited from a lower energy level to a higher energy level, the atom had absorbed a photon with energy equal to the difference in energy levels. When a particle and its antiparticle annihilate one another, 2 photons, gamma rays, get emitted. Photons are stable particles. The cosmic microwave background, CMB, is photons that were emitted 380,000 years after the Big Bang and have been traveling at the speed of light for 13 billion years, not having interacted with matter. Toward the end of the course, we cover light, photons, and two-slit diffraction of both photons, electrons, atoms, and molecules acting as waves. If you like, you can jump to that material and then return to here. The W plus and minus weak bosons, shown in this cell with charge plus or minus 1, mediate the weak interaction or weak nuclear force that transmutes the flavors of quarks, and leptons. The weak interaction is responsible for radioactive beta decay of unstable radioactive nuclei and for initiating nuclear fusion in the Sun. These bosons have heavy masses, 80 billion electron volts, 80 times the proton's mass, and lifetimes less than 10 to the minus 24 seconds. The W boson is 2 particles, W plus and W minus, antiparticles to one another, but it's always shown as one cell in this diagram. The weak interaction changes the flavor of quarks and leptons. We will see examples of this. The weak interaction only acts over a short range, shorter than the size of a proton. This is sometimes called the weak nuclear force or weak force. However, it is not an attraction or repulsion. So not a force that causes an acceleration, and it does not produce bound states. The Z boson is electrically neutral, zero charge, so it does not change the charge of particles. It also does not change particle flavor, but it does change particle momentum. It produces the neutral weak current and mediates elastic scattering between neutrinos and matter. We will not cover the Z boson in the rest of this course. Gravitation is a fundamental force acting on all particles, even those with zero mass. Gravitation is the realm of general relativity, outside of the standard model of elementary particles. So there is no graviton particle in the standard model. At the top of the rightmost column is the Higgs boson. This is an excitation of the Higgs field, which gives charged elementary particles their masses. The Higgs field pervades all space in the universe. The Higgs boson has spin 0 and is called a scalar boson. The Higgs boson has high mass, 125 billion electron volts. There could be other undiscovered Higgs bosons of higher mass, and that would not violate the standard model. The Higgs field is responsible for giving W and Z bosons, quarks, and the charged leptons their masses, but not, I believe, the neutrinos. This is beyond my understanding. For our purposes, we just need to know the particles' masses, not how the Higgs mechanism works. The Higgs boson is sometimes popularly called the God particle, but not by physicists. We will not cover the Higgs boson or the Higgs field in the rest of this course. So we're done with the Higgs boson and we're done with the Z boson, but we have more to learn about the other particles. Antimatter and antiparticles. This chart is for the matter version of the elementary particles. Each fermion also has an antimatter version with the same mass and spin, but negated electrical charge, and for quarks, negated color charge, which we have not talked about yet. Here is an expanded chart showing the antifermions. The antiparticle version of a fermion is usually given the prefix anti. For example, here's the up quark, which is a matter quark, and here is the anti-up antimatter version. And it's usually shown with an overbar over the particle symbol. The particle symbol for up is U, and the particle symbol for anti-up is U bar, U overbar. However, the antiparticle for the electron, the anti-electron, is always called the positron, and it's represented as E+. The photon is its own antiparticle, but don't think that two photons annihilate each other. The gluon is its own antiparticle, and the Z boson is its own antiparticle. The W plus and W minus are antiparticles to one another. They can annihilate each other. I don't believe it matters which is considered matter and which antimatter. I've never seen the concept of antiparticle used with respect to the Higgs particle. Remember that the left three columns are the fermions. The top two rows of fermions, shown in purple, are the quarks, the building blocks of protons, neutrons, etc. More on these later in the course. The bottom two rows of fermions, shown in green, are called leptons. The 6 particles are the 6 flavors of lepton, which can be transmuted one to another by the weak interaction of the W bosons, as we will see later. Leptons are not subject to the strong interaction that is mediated by gluons. Gluons glue quarks together, not leptons. Let's look at the electron row. From left to right, we have electron, muon, and tau. These are all spin 1/2 fermions with electrical charge of -1 elementary charge unit. The muon is 200 times more massive than the electron, and the tau is 18 times more massive than the muon. One property not shown in the elementary particle chart is lifetime. The electron is a stable particle. It is known to live at least 18 orders of magnitude longer than the age of the universe. I believe that most of the electrons in your body have been in existence since the first minute after the Big Bang. The electron is stable because there is no lower mass particle of charge -1 for it to decay into. The muon and tau have the same physical properties as the electron but are more massive, and they have finite lifetimes. They are not stable. The muon's lifetime is 2 microseconds. The heavier tau's lifetime is less than a trillionth of a second. The muon and tau decay into an electron, which we will see in a bit. We won't be covering the tau particle further in this class. With some effort, it is possible to put a muon in place of the electron in a hydrogen atom for a little while. Since the muon is more massive than the electron, the energy levels change because these depend on the mass. Physicists use this to measure the proton's radius. Now, this may be the first time you've ever heard of muons, but You have been irradiated with muons your whole life. High-energy cosmic rays from our galaxy and the universe constantly hit Earth's atmosphere. Some collisions produce muons traveling near the speed of light. About 10,000 muons reach every square meter of Earth's surface per minute. This is part of the natural background radiation that we experience throughout our lives. If you are particularly attentive, mathematical, and skeptical, you might say, now wait a minute. How can a muon that only lives for 2 microseconds travel through miles of atmosphere? Isn't that going faster than the speed of light? The answer is that the created muon's kinetic energy is so high that it is traveling near the speed of light, and we need to take into account time dilation and length contraction of special relativity. This is a common exercise given in special relativity classes. The muon's magnetic dipole moment G-2 experimental results currently disagree slightly with the quantum field theory calculation, which is hyped in the news these days, and we will talk about more at the end of the course. More about electrons later in the course. Neutrinos and weak interactions. These 3 particles are the neutrinos. Next, we discuss the electron neutrino at the lower left of the chart. The 3 neutrinos, electron neutrino, muon neutrino, and tau neutrino, have 0 electrical charge, so they are not affected by electrical attraction, magnetism, electromagnetic fields, or photons. Neutrinos interact with other particles solely via the weak interaction, which transmutes the flavors of quarks and leptons. We will see some examples later in the course. Electron neutrinos get created and emitted prodigiously in the nuclear fusion that occurs at the core of the Sun. The electron neutrino rest mass is so small, less than 1 electron volt, and the fusion reaction releases so much energy that the kinetic energy with which the electron neutrinos get emitted is ultra-relativistic. They travel near the speed of light. It turns out that the interaction cross-section between neutrinos and other elementary particles is so small, so infinitesimal, that the emitted neutrinos travel straight through the layers of the Sun, hardly interacting at all. 8 minutes later, some of those neutrinos arrive at the Earth and travel straight through the Earth. Trillions of neutrinos from the Sun pass clean through your body every second of your life, day and night. It is difficult but not impossible to detect neutrinos. One Neutrino Observatory is located underground at the South Pole and is called Ice Cube. It is possible to detect neutrinos from the Sun, but also from the entire universe. The lifetimes of neutrinos are unknown, but they may be collectively stable. Neutrinos constantly pass through the Earth that may have been emitted in the first minutes after the Big Bang, and have been traveling near the speed of light ever since, passing through galaxies, stars, and empty space, hardly ever interacting with matter. Not black holes, however. If a neutrino passes across a black hole's event horizon, it cannot escape. It may be that the number of neutrinos is 1,000,000 times the number of protons in the universe. The number of photons is much higher than that. It turns out that neutrinos have a strange, unique property that no other elementary particle has. An electron neutrino does not stay an electron neutrino forever. Neutrinos continually oscillate their flavor between electron neutrino, muon neutrino, and tau neutrino. Very strange. The tau and muon neutrino do not have finite lifetimes for decaying permanently to an electron neutrino because the neutrinos forever oscillate their flavor. Not only is this strange, it complicates the detection of neutrinos, because a given detector can only detect one of the flavors. The other flavors just pass through. Look at the masses of the neutrinos. For other particles, the mass is either 0 or it's given as an approximate number. However, for the neutrinos, the three entries give an upper bound for the mass less than 1 electron volt, less than 0.2 million electron volts. It turns out that it's not possible to measure these three masses separately because of their flavor oscillations. It's complicated. Because the electron neutrino mass is so small, electron neutrinos are generally relativistic, traveling at a good fraction of the speed of light. The highest energy neutrino yet detected on Earth was 6 by 10 to the 15 electron volts, higher than the Large Hadron Collider can achieve, but still orders of magnitude lower than the highest energy cosmic rays. Conservation of lepton number. Lepton number is the number of matter leptons minus the number of antimatter antileptons. Lepton number is conserved in every interaction since the first minute after the Big Bang, or that's what physicists believe. In addition to lepton number, there are lepton family or flavor numbers. Electron number is the number of electrons plus electron neutrinos minus their antiparticles. Likewise, muon number and tau number. Lepton family numbers are only approximately conserved. They are not conserved in neutrino oscillation. Muon decay. The muon lifetime is 2 microseconds. Here is the normal decay for a muon. A negatively charged muon decays via the weak interaction to a negatively charged electron plus an electrically neutral electron antineutrino, the E for electron, the nu for a neutrino, the overbar for an antiparticle, so electron antineutrino, plus a muon neutrino. Electrical charge is conserved. It is -1 on both sides. -1, -1, 0, 0. Lepton number is conserved. It is 1 on each side. 1, 1, -1, 1. Muon number is conserved, it is 1 on each side. 1, 0, 0, 1. Electron number is conserved, it is 0 on each side. 0, 1, -1, 0. This is a correct representation of muon decay, but we could dig deeper. Firstly, this decay is due to the weak interaction, which is mediated by the W plus and minus bosons, but we don't see these bosons in the decay equation. Secondly, the equation creates 3 new particles on the right-hand side. Usually this means that there's an underlying mechanism that first produces 2 particles, and then one of those particles decays to produce 2 particles. And seeing this mechanism can give us insight into the process. Here is the Feynman diagram for the dominant muon decay mode. In this particular diagram, time flows vertically from bottom to top, and the horizontal direction is space. We start at the lower left. An electrically negatively charged matter muon is moving to the right. At this interaction vertex, the muon decays to 2 particles via the weak interaction. The dashed segment to the right is a negatively charged W minus boson. The line toward the upper left is an electrically neutral matter muon neutrino. The first vertex conserves electrical charge -1, lepton number 1, and the lepton family numbers. Then at the second interaction vertex, the W minus boson decays into 2 particles via the weak interaction, an electrically negatively charged matter electron and an electrically neutral antimatter electron antineutrino. Antimatter particles are given an arrow direction pointing backward in time. This second vertex conserves electrical charge -1, lepton number 0, and the lepton family numbers. After the second vertex of this Feynman diagram, the 3 remaining particles match our previous decay equation. Without the W minus boson. We have an electron antineutrino, and a muon neutrino. However, if you think about it, there's something pretty odd about this Feynman diagram. Do you see a problem? The rest mass of the original muon is 106 million electron volts. The rest mass of the W minus particle is 80 billion electron volts, 800 times more massive than the muon. Does this weak interaction violate the conservation of energy? Sort of yes, sort of no. In classical mechanics, total energy is always conserved at all times. In quantum field theories, energy fluctuates over short times. The interaction can borrow energy from the vacuum and then shortly return it within limits. Particles created from the borrowed energy are virtual particles, with the same properties, mostly, as real particles, except the particles are very temporary. There is a borrowing time that depends on the amount of borrowed energy. This interaction can borrow 80 billion electron volts from the vacuum to create the virtual W- boson, but that boson must vanish and return the borrowed energy within 4 × 10⁻27 seconds. In that interval, the virtual W- boson could move no more than 1 × 10⁻18 meters, 1,000th the radius of a proton. After this fleeting time and distance, the virtual particle vanishes and the energy is again completely conserved. If this view is discomfiting, the Feynman diagram is a useful explanation of the three emitted decay particles obeying conservation rules, but they can be considered to have been created simultaneously with no borrowing of energy from the vacuum. So, when I said earlier and continue to say in this course that the weak interaction is mediated by W+ and W- bosons, we should understand these as being virtual W+ and W- bosons. On a Feynman diagram, a line between two vertices, whether a straight line or a wavy line, represents a virtual particle, an interaction mediating virtual boson. Strange, but this is the current understanding due to quantum field theory. It will turn out that the high mass of the W bosons and the resulting short time for borrowing that energy from the vacuum will be responsible for the slow and steady pace of nuclear fusion in stars comparable to the Sun. Quantum electrodynamics says that every real electron is surrounded by a small cloud of virtual electron-positron pairs continuously popping in and out of the vacuum. The electron-positron pairs get separated or polarized by the electron's charge. They screen the electron's naked charge, and the universe only sees the screened charge. This actually has a small measurable effect on how much of a magnet an electron is due to its electrical charge and intrinsic spin angular momentum, the electron's magnetic dipole moment. G-2 experiments agree with this virtual particle pair theory for the electron to 13 significant figures, the most successful result of any scientific theory and experiment. However, the experimental value for the muon disagrees slightly with the theoretical calculation, possibly due to virtual quark-antiquark pairs, and this is in the news these days. The vacuum is not nothing. The vacuum is a sea of particle-antiparticle pairs continually created from the vacuum and returning to the vacuum. Once you understand the Feynman diagram, you're no longer supposed to think of it as events in time. Each Feynman diagram tells physicists the probability amplitude for that particular distinct outcome. They don't dwell on the times of energy borrowing. Quarks. Let's look at quarks. The 6 purple cells. 2 rows of 3 columns, which are the generations 1, 2, and 3. The 6 particles are the 6 flavors of quark. All 6 are spin 1/2 fermions. All 6 are attracted to one another via the strong nuclear force mediated by gluons. The first row is the up quark, the charm quark, and the top quark, U, C, and T. 3 generations with progressively higher mass. These 3, in row 1, have electrical charge plus 2/3 elementary charge units. That is, opposite in sign to the electron and 2/3 the magnitude of the electron's charge. The second row is the down quark D, the strange quark S, and the bottom quark B. 3 generations with progressively higher mass. These 3 have electrical charge minus 1/3 elementary charge units. That is, the same sign as the electron and 1/3 the magnitude of the electron's charge. The top and bottom quark were also called truth and beauty initially, decades ago, and some physicists today use top and beauty instead of bottom. The top quark is the highest mass elementary particle at 173 billion electron volts. Quarks are point-like particles with size less than 10 to the minus 19 meters, so less than a 10,000th the size of a proton. Quarks are subject to the strong nuclear interaction, also called the color force, mediated by gluons. Leptons are not. Gluons glue quarks together, not leptons. The weak interaction W plus and W minus bosons can transmute the flavor of a quark, changing a quark from the first row into any quark of the second row, or vice versa, always changing its electrical charge by 1 unit. Each of these 6 quarks has an antiparticle with the same mass and spin, but opposite electrical charge. These are represented with an overbar over the letter of the quark. The U-bar anti-up quark to the U up quark has charge minus 2/3. The 4 top, bottom, charm, and strange quarks are unstable, and they decay in less than a microsecond via the weak interaction, ultimately to an up or a down quark, per the following diagram. On this diagram, the horizontal axis is charge, and there are 2 charges for these matter quarks. The first row, up, charm, top, has charge plus 2/3. The second row, down, strange, bottom, or beauty, has charge minus 1/3. The vertical axis is mass on a log scale because the mass of the top quark is so much higher than the mass of the up quark. The strongest decay path is within a generation, from the higher mass to the lower mass quark within that generation, shown as solid black arrows. The top quark almost always decays to the bottom quark, generation 3. The charm quark usually decays to the strange quark in generation 2. The down quark decays to the up quark when a down quark can decay. For example, a neutron decaying to a proton. It is not that every down quark decays to an up quark. The proton, which we'll learn is an up quark, down quark, is stable. Its down quark does not decay. Now, bottom and strange, they cannot decay within their generation. They do decay to a lower mass generation. Bottom to charm or up, strange to up.